Hey guys, my name is Noah Hogan, and today I will be exploring carbide nanoparticles with you. So first, I will go through a little introduction. I will show you what nanoparticles are, and then we'll go through a history of nanoparticles, so the first usage of nanoparticles and how they apply today. Then we'll go through the structure of carbide nanoparticles specifically. I'll go through some manufacturing processes, so we'll learn how these particles are made. Then I'll go through some properties of carbide nanoparticles, and we'll look at some applications today. So what is a nanoparticle exactly? Well, a nanoparticle is a very small particle with a certain shape, and it can range from 1 to 100 nanometers in one dimension. So as long as the x, y, or z component of the particle is 1 to 100 nanometers in size, it is considered a nanoparticle. So, to give you an idea of the scale of these particles, if you take a nanoparticle and you compare it to a soccer ball, that is the same size difference as the ratio of the size of a soccer ball to the size of the entire Earth. So these are very, very small particles. And they can have different interactions with light. They have a lower melting point than their corresponding materials usually. And they also have different chemical properties from their original materials. They're usually exploited because of their large surface area to volume ratio. So these particles are so small in size that if you have a lot of them, they have a big surface area, but they have a very small volume. And they're also involved in different industries. So health, electronics, and catalysis are three major industries that these particles are involved in. So, in the 5th century BC, Greeks and the famous philosopher Democritus first characterized nanoparticles. They theorized that there must be an underlying component of matter that defines all physical objects. Democritus called these units of matter atomos, which means unbreakable in Latin. This is the first time that anything was defined at the nanoscale. Also at this time, dichoric glass is something that was being manufactured, which uses nanoparticles to change color when light shines on the glass. So what happens is nanoparticles inside the glass reflect light while still allowing some light to pass through the glass. So it gives it a different color in ambient light than it does in darkness. In 1959, Richard Feynman published his famous paper, There's More Room at the Bottom, which theorized that atoms could be manipulated by future scientific tools, spurring on the field of nanotechnology. Now, Norio Taniguchi was the first person who formally defined nanotechnology, and he described the manufacture of materials so small that they could be measured only on the nanometer scale. CDOTs are favorable materials for applications in bioimaging, biosensor, and drug delivery. So there's something to look forward to in the future of nanotechnology. And I'll explain some more applications of these nanoparticles in my later slide. To characterize the structure of carbide nanoparticles, I will be looking at titanium carbide with you guys, which is a popular carbide used for microwave absorption, electromagnetic protection, energy conversion, and catalytic properties. So this has a face-centered cubic structure, which is an NaCl type structure, and it belongs to the FM3M point group. Now, these titanium carbides can be seen as a solid solution with carbon atoms as the solute dissolved into the titanium crystal cells. And carbon atoms occupy the interstitial spaces between the titanium atom. The small size of carbon atoms in titanium carbide give the carbon a good amount of mobility, which means that point defects, such as Frankel and interstitial defects, are common, and a perfect stoichiometric ratio of titanium to carbon is not commonly seen. So to further characterize the structure of the particles, I have included a picture of the typical growth structures of titanium carbide on this slide, as well as a supercell of a titanium carbide molecule, so you guys can see what these molecules look like together. So the typical growth mode of titanium carbide nanoparticles is typical faceted growth. But if we manufacture it differently, it can adopt different growth structures, such as cubes, truncated octahedrons, sphericities, dendrites, terraces, and even different dimensional morphologies. So there are really a lot of different shapes that these nanoparticles can develop. Now, the crystal structure, which we defined in the previous slide, is not the only factor that can control the growth behaviors. There are certain intrinsic and extrinsic conditions that can be modified to forecast and control the growth of these carbides. Now that we have an idea of the underlying components that define nanoparticles, in the further slides I will go through some of the processes that are used to manufacture these particles. So there are many ways that we can manufacture nanoparticles, but they usually fall into two categories. So one of those categories is the top-down process. In this process, we take bulk materials, we refine that material down to powders, and then we further refine that powder to get the nanomaterial size that we're looking for. One method to do this is ball milling, but we also have thermal evaporation, laser ablation, and all of these different techniques have certain advantages and disadvantages associated with them. So I will go further into detail with the ball milling technique. This is a simple and efficient process that is used to really create nanoparticles at a large scale. It involves the principle of attrition, which is the process of transferring kinetic energy from the grinding medium, so the balls that we're using, to the bulk material that we're trying to reduce down. One of the ways that these balls perform this is by temperature and pressure created by the interaction between the balls and the compound we are looking to grind. And this can cause phase transformation at a high temperature as well. So basically, if you know what a rock tumbler looks like, we take the balls, which is the grinding medium that we would use in a rock tumbler, and we put it in this vessel, and the vessel rotates for a long time, and we put in our bulk material, and that bulk material eventually gets ground down by these grinding balls until we get it to the size that we want. Now, some advantages of this technique is that it has a very high capacity, and it's a very universal technique, so we can use it pretty much anywhere. The mills last a long time, and they require little maintenance, and it's a very simple process. It's reliable, and it is very safe. Also, we can use it if we have stacked materials. So what we can do is we can reduce the thickness of those materials and break them down further. Some disadvantages of this process are that the majority of ball milling treatments are destructive. So we disorder the crystal structure and we introduce a large amount of flaws, which is not ideal. And it's a big reason why this isn't used in manufacturing nanoparticles if we want more accuracy with the structures that we're producing. The mills are also very weighty, and the grinding uses a lot of energy because there is a lot of wear on the balls, the mill walls, friction, material heating, and all of that stuff contributes to the energy usage of the mills. There is also a lot of contamination and noise during the process that we use to make these nanoparticles. So the other main group of manufacturing processes that are used to create nanoparticles is the bottom-up process. So this involves taking particles of atomic size, so we're taking atoms here, molecules. We transform them into clusters of atoms and molecules, and those are further scaled up to the nanoparticle size. So methods in which we can do this are chemical vapor deposition, the hydrothermal method, coprecipitation, and sol gel. And I will go through the sol gel process really quick because that's the most commonly used process to create metal carbides. So this is a process in which a solution made up of solid particles, which is how sol gel gets the sol part of its name for solid. We suspend that in a liquid, and then the gel is a certain macromolecule mixture that also is dissolved in the liquid. So the first step of the process is hydrolysis of the metal oxide or whatever metal compound that we're using. And then we condensate that metal with neighboring molecules of the gel matrix. And then the third step is further condensation of the metal, and we precipitate the gel out. And after that, the gel is dried. And the drying process is super important to the sol gel manufacturing process because different ways that we dry the gel can give the nanoparticle different properties. So if we thermal dry the gel, it gives zero gel. Supercritical drying, we can get aerogels, and freeze drying is used to get cryogel, which has an impact on the gel network structure. After that, calcination is carried out to get rid of all of the water molecules and residues from your sample. And again, temperature is super important in managing the density of your nanoparticles and the pore size of your final material. So, to give an example of a metal carbide being synthesized this way, I am going to use a paper in which they transform silicon dioxide into a silicone carbide nanoparticle. So what they did is they prepared a silicon dioxide gel or solid with ethyl orthosilicate, absolute ethanol, and they deionized the water that they were using as raw materials. They used hydrochloric acid to speed up the dissolution process of the silicon dioxide. And then they impregnated the material with rattan. And this is super cool because it is the bamboo-like grass that they use, and it's like the stems of a palm. So they impregnated the silicon dioxide solid to obtain a silicon dioxide sol gel rattan mixture, and then they pyrolyzed that mixture to create our silicon carbide. So after they did that, they put the gel and rattan mixture into a crucible, and this is where drying occurs. So they covered it with a lid, and they placed it in a vacuum, high-temperature tube furnace. They held the furnace at a certain temperature for 120 minutes under an argon atmosphere, and then they let it sit for a couple of days, and that's how they got the silicon carbide nanoparticle. So a super cool process using a bamboo material. I just thought that was really interesting how they use the organic material to create the nanoparticle. But that is how nanoparticles are created from atoms, and they scale them up to create the final nanoparticle. While both the top-down and the bottom-up processes are necessary to create nanoparticles and they're currently the industry standard, they do have some problems. The conditions to produce the carbide nanoparticles are harsh, mostly inaccessible, and they only produce a small amount of nanoparticles at a time. So a novel method to create nanoparticles, which is called mild solution phase synthesis, might be the answer to this problem. This is a mild method, and it's scalable, so we can produce lots of transition metal carbides at a time. I will be going over a paper that deals with molybdenum carbide. So these researchers took a precursor solution of molybdenum hexacarbonyl, OAM, and ODE, and they heated the mixture to 140 degrees Celsius in a nitrogen environment. Now 140 degrees is a lot less than what they usually use to create these carbides, so that's where the mild solution part comes in. Then they cooled the solution to 100 degrees Celsius, and they transferred it to a glass syringe. What they did after that is they connected the inlet tubing of the glass syringe to an MF reactor, and the resulting molybdenum carbide nanoparticle suspension was combined with hexanes in a 1:5 ratio of hexanes to create the reaction mixture, and that was transferred to centrifuge tubes. After that, they obtained the black nanoparticle pellet that they were looking for, and they redispersed it with carbon trichloride to further wash and process the nanoparticles. After that, they dried the suspension, and they redispersed it in carbon tetrachloride to resuspend it, and then it can be used for whatever purpose you want. So now that we know what nanoparticles are and how we create them, we'll go over some properties of these nanoparticles and how they're used in some modern-day applications. The first carbide nanoparticle that we'll be going over today is molybdenum carbide. This is actually the carbide that we just produced in mild solution phase synthesis, so we'll get to see some really cool properties and uses of this compound. So some of the properties of molybdenum carbide are its high thermal stability, high electrical conductivity, its absorption capacity, high melting point, and its high relative hardness. So it has lots of mechanical uses, and also chemically, it is resistant to nitrogen and sulfur. It has a high catalytic current density, and its durability is similar to those of noble metals, which allows us to use it in many catalytic reactions. Some of those catalytic reactions are the hydrogenation of carbon dioxide to alcohol. Also, the hydrogenation of carbon monoxide to alcohol can be performed by molybdenum carbide nanoparticles. We can also perform a process called hydrodeoxygenation. Wow, don't make me say that one again. Which removes oxygen from oxygen-containing compounds. Finally, we can perform electrocatalytic hydrogen evolution from water splitting, including the oxygen evolution reaction, hydrotreating, water gas shift reaction, hydrodesulfurization, CH4 aromatization, and hydrodenitrogenation. So these are all hydrogen evolution reactions that we can perform with molybdenum carbide nanoparticles. And finally, we can perform electrocatalytic reactions with molybdenum carbide. So it is a very diverse carbide nanoparticle compound that has many industrial and chemical uses. The next nanoparticle carbide that we'll go over is silicone carbide. So silicone carbide has a very versatile surface chemistry. It can fluoresce from the ultraviolet to the near-infrared spectral range, and its size can be tuned from 1 to hundreds of nanometers. So very versatile with the chemistry that we can do with it. It also has outstanding thermal conductivity, as well as thermal, mechanical, and chemical stability, which allows it to have a low toxicity and biocompatibility. It's a wide bandgap semiconductor, so it can be used in many electronic applications. And it can also be used as an initial material for ceramics and composites, as an abrasive. It can be used as catalyst support, photocatalyst. It can be used in certain biosensors, absorbance, and it can be used as optical probes in biology. And that last one, the application of optical probes, I will go over in the next slide. So one of the really cool applications of silicone carbide nanoparticles is cellular imaging, and there was actually a really cool paper outlined by Zhao et al. In which they labeled human mesenchymal stem cells with silicone carbide nanoparticles, and they used it to observe the life cycle and morphology of those cells. To do this, they plated the human mesenchymal stem cells into a 6-well plate, and they grew the cells until they were fully confluent, which means they covered the entire culture vessel. Then they took 2 milliliters of the silicone carbide nanoparticles, and they added that into the cell media at different concentrations. After the cell media and the nanoparticles were allowed to incubate for a certain period of time, the cells were washed with PBS to remove the free nanoparticles, and then they were collected. The cells plated in other wells were treated with a dipogenic or osteogenic induction media for 3 weeks. After this, the cell morphology was recorded with photoluminescence imaging on different days for 3 weeks. The morphology changes were also recorded with bright field and photoluminescence imaging. So in this method of imaging, we use light energy to stimulate the emission of photons from the labeled cells, and we collect that data and we can graph it or use it in images, which we'll see in the next slides. These are some figures that Zhao et al. Used to characterize their findings from the experiment. So the left figure shows the photoacoustic properties of silicone carbide nanoparticles, and this is plotted at different concentrations. So we can see, here I'll circle it for you. So we can see that a higher concentration, so the number at the end represents the concentration of the carbide nanoparticles, it correlates with a greater amount of photoacoustic emission. So the more concentrated the nanoparticles are, the more intense the emission is. for the photoacoustic imaging. In the right figure, it shows the absorbance spectra of the silicone carbide nanoparticle suspension, and that is shown in figure A. Figure B shows the excitation spectra of the silicone carbon nanoparticles. Figure C shows the emission spectra at varying excitation wavelengths of the silicone carbide nanoparticle suspension. So we can see at different wavelengths the RFU changes depending on the concentration and the wavelength being observed. And in figure D, it shows the emission spectra of dry silicone carbide nanoparticles using an excitation source of 325 nanometers. And again, we can see that the different emission spectra changes with the concentration of silicone carbide nanoparticles that we use. Now, this is where the experiment gets super cool, because this is where we can actually see the fluorescent properties that the silicone carbide nanoparticles possess. So in the left figure right here, we have different types of cells, including the labeled human mesenchymal stem cells. So those are the top two rows right here. And these cells were labeled with the 620 micromolar silicone carbide nanoparticle solution. So what these graphs show is that the stem cells are still visible under fluorescence microscopy 11 days after labeling. And this shows that there is a really long-term cell imaging ability of these nanoparticles. What's really cool is that we can actually see the labeling of the stem cells even after they differentiate for a short period of time. So it's a really long-term process that can help us look at cells and see their development. Also, these bottom two rows show the cell labeling in adipocytes and osteocytes. And these we can actually see for 3 weeks after labeling. So that is just super cool, very long-term imaging method that we can use these nanoparticles for. In the right figure, they tracked the 620 micromolar silicone carbide nanoparticle suspension in a mouse. So this is done in vivo. And they use photoacoustic imaging at varying cell concentrations to characterize the images. So these labels represent the injection concentrations in cells per microliter and the photoacoustic intensity of the injected silicone carbide nanoparticles were at a wavelength of 770 nanometers. So a really cool takeaway from this figure right here is that we can still see the nanoparticle implants in the cells over a period of 14 days. So even in vivo, this is a super long-term cell imaging method that is biocompatible and very, very long-lasting. So it can have very big medical implications that could help us in the future. Finally, we're going to take a look at iron carbide nanoparticles, and we will discuss some of their applications in modern-day technology. So the properties of iron, which are its metal and chemical activity, and the unique properties that carbon possesses. So carbon has a very high biocompatibility. I mean, we're made of carbon, so it makes sense. And its relative inertness make it a great candidate for biomedical applications. So some of the catalytic applications that we can use iron carbide nanoparticles for is the Fischer-Tropsch synthesis, which converts a mixture of carbon monoxide and hydrogen into liquid hydrocarbons. So this is a super, super popular synthesis used in a lot of industrial applications. We can also use it in oxygen reduction reactions, electrocatalysis, batteries, and supercapacitors. So lots of different applications ranging from biomedical applications to catalysis and industrial applications. So what I'm going to focus on is the properties of these magnetic nanoparticles and their application in the biomedical field. So some of the medical imaging techniques that we can use these particles for is MRIs, so magnetic resonance imaging, magnetic hypothermia, which is abbreviated as MH, magnetic targeting, magnetic separation, magnetofection, biosensors, and tissue engineering. So as you can see, there is a wide array of applications that iron carbide nanoparticles has in the medical field. And the reason this happens is because the iron carbide nanoparticles have what's called a high magnetic saturation value. So this is the state that's reached when an increase in a magnetic field applied to the compound cannot increase the magnetization of the material further. So in essence, the material is saturated with the applied magnetic field. So the flux density of the material levels off, so we can't add any more magnetic field to change the flux density of the compound. And it also has a low toxicity, so it's very biocompatible, which means we can use it in our bioimaging techniques. So what some researchers found is that iron 5 carbon 2 carbide nanoparticles have twice the magnetic saturation values compared to iron oxide nanoparticles, which are currently used in MRIs and MH imaging techniques. So we get greatly improved performance in both of those techniques when we use iron carbide nanoparticles. And in the next slide, I'll go into detail about how that entire process works. To explain some of the properties of iron carbide nanoparticles, I think it's helpful to look at some medicinal applications of these particles, particularly with MRI technology. So you have a lot of protons in your body, and when you get an MRI, all of these protons are aligned with an external magnetic field. After this occurs, a radiofrequency current is introduced, which induces a shift in the alignment of your protons with the external magnetic field. So your protons are spinning, you get a radiofrequency current, and the direction of that spin changes. This is called a spin echo pulse sequence, and when this happens, all of the spinning dipoles are in phase. After that, the T2 relaxation occurs, which is a dephasing of the spinning dipoles, resulting in decay of the magnetization of the transverse plane. So basically, all of the spins of your protons are aligned, but it's straining against the magnetic field. So after the radiofrequency current stops, your protons will realign with the magnetic field, and that will release energy, which can be captured, and it allows us to image your organs or whatever we want to image. So shortening the time in which this T2 relaxation occurs can be used to improve the signal to noise ratio in an MRI. So basically we can get better contrast images if we shorten the time it takes for these protons to go back, because then we can apply more pulses and use a higher magnetic field with a shorter response time. So according to the quantum mechanical outer sphere theory, and I have the equation on the slide here, this property is highly dependent on the magnetic saturation of the magnetic nanoparticles, which I discussed in the previous slide. So what's really, really cool is that iron carbide nanoparticles have a higher magnetic saturation, which means we can achieve better contrast with them than with the iron oxide nanoparticles that are currently used with MRI technology. So they actually did in vivo testing with this with livers and mice, and the results were that the images in the livers were much darker than those injected with the iron oxide nanoparticles. So another cool property of iron carbide nanoparticles is that they are light responsive, which means they can be used as probes for fluorescence imaging. So that is another imaging tool these nanoparticles can be used for in biomedical applications. Also, they can convert light energy into other energies such as heat or ultrasound, which means they can be used as agents for photothermal therapy, which is another medical use of these compounds. So the magnetic, fluorescent, and the biocompatible properties of iron carbide nanoparticles make them have really, really great promise in biomedical applications. And we can really do many modes of diagnosis and further therapy for whatever medical needs we might have with these particles. So they're just super cool. So that concludes my presentation on carbide nanoparticles. I hope you guys learned a little something. I definitely love researching anything that has to do with medical applications of these unique particles. So learning about MRIs and the silicone carbide nanoparticle imaging I just found super, super interesting, and I hope you guys did as well. Some of my resources are located on the slide, so if you guys want to check out those scientific papers further, they are right there for you. I hope you guys have a great day, and thank you for your time.